like lying.
Yeah, but why?
I was lying in bed and I was so comfortable.
How could you lie on such a sunny morning?
Exactly, it's too funny.
Sit down. I don't have many of my students complain that it's too sunny. Right, Newton's law. Okay. Yeah, a little bit more on this one. Right, so the first one, what is the gravitational force between two masses of a kilogram each and a meter apart? So, let's open up the calculator. What constant? Oh, thank you. Constant is 39.
6.67.
Yeah, well, it's on the calculator. M1, M2 over R squared. So you realise, oh, it's just going to be G. It's tiny, tiny force. Tiny. So if I have 1 kilogram and 1 kilogram and they're 1 meter apart, then the gravity force between them is tiny, absolutely tiny. Yeah. What's the gravity force between two equal masses of 10 to the 6 and also a meter apart? Okay, so I'll just change this to 10 to the 6. 10 to the 6. What's 10 to the 6? That's 1,000 kilograms, isn't it? 1,000 tons. Yeah. No, that's... Well, I mean, it's not hard to imagine 1,000 kilograms, 1,000 tons. I mean, it's obviously pretty big, but it's not like the size of a planet. You know, it might be like the size of, I don't know, might be 1,000 tons. Would it be a building? Maybe? No. Mountain, maybe? Yeah. Yeah, something like a mountain, a small mountain, maybe. So you can see, okay, now we're starting to get big enough that we could actually see a force of 66 newtons. Yeah, but you got to remember, you don't feel it only because the Earth, which is under you, is so much bigger in comparison. If you could imagine you had the mountain and then the Earth somehow disappeared, then you would actually feel the force pulling you towards the mountain. But it's just because the Earth is so big, whatever force it has is so much more than the mountain. And anyways, you're not going to be 10 to the 6. You're probably less than 10 to the 6, your mass, I would imagine. Now, I know you're not 10 to the 2, obviously, but just to make it easy for me to type in. You see, that's 6 millinewtons. It's tiny. Yeah. Okay. Next one. What is the velocity of the Earth as it orbits the Sun? Yeah, it's kind of like the question I gave you with the electron that circles the proton. So, you have, where's my pen? You have the Sun, and you have the Earth, and you have F equals ma, which equals mv squared over r. So therefore, the v equals fr over m square root. But our buddy Newton has given us a formula for f. He says it's g m over r squared or over m. Where, just to be clear, this is big M and this is small m. So that's nice, because that will cancel with that, and that will cancel with that. So we're just left with root gm over r. Let's see what we get. Root gm over... Now, I've given you the info down the bottom. Mass of the Sun and radius of the distance between the Earth and the Sun, 1.5 times 10 to the 11. And then mass of the Sun, 1.99 times times 10 to the power of 30. 29.8 kilometers per second.
But
Yes?
I use different way.
Did you get the same answer?
But different.
What did you get?
28.9.
20 what?
28.9.
What did you do?
I used the V equal omega r
Yeah.
equal 2 pi r over t.
Ah!
I use t equal just
Yeah, that would work too.
Is it okay?
Yeah, well, why is your answer slightly different to my answer? And which answer is better?
Both of
Oh no. Well, if your answer's fine, in the exam you would still get full marks. But in real life, which answer is better?
Okay.
Well, naturally, but why?
I don't know that.
You see, Wookie did it a way that used the time. T equals 2 pi over omega. Why is my answer a little more accurate than his answer?
Oh, t is not exactly this.
Yeah, T is not exactly 365. It's 365.25. So I think that's why your answer is a bit different to mine. But in the exam, that doesn't matter. Okay, continue. Yeah, next one. How far does a spaceship need to be from the Earth so the total force acting on it from both the Earth and the Moon is 0? Okay, so in this one here, you have the Earth, you have the Moon, and there's some point here where the distance between the Earth and the Moon is not the same, but what is the same is the force pulling it to the Earth is the same as the force pulling it to the Moon. Now, just to be clear, we'll call this one M1, we'll call the spaceship M2, and we'll call the Moon M3. So the force here would be G M1 M2 over, now we have to give some letters here, so yeah, I'll call this distance here X, and this one will be R minus X. Yeah? So that would be X squared. And that should equal G M2 M3 over R minus X squared. Okay, well then that's nice because cancel. Cancel. Yeah, I'll rearrange, so I'll say M1 R minus X squared equals M3 X squared. Okay, so next I'll square root. I have square root M1 R minus X equals square root M3 times X.
It's good.
It's better. Did you
Yeah.
expand?
Yeah.
Yeah.
Terrible.
Not terrible, just painful. So, root M or root M1 minus root M1 X equals root M3 X. So that means, therefore, X equals or root M1 over root M1 plus root M3. So let's calculate that now. What is the radius? Distance between the Earth, between the Moon and the Earth, 385,000. Square root.
No, not exactly that. That's kilometer.
So that, oh, thank you. What's the mass of the Earth?
5.97 by 10 to the 24.
Okay, and then 5.97 times 10 to the power of 24 plus root 5.9, no.
No, 7.34 by 10 to the 22.
385,000 kilometers. Huh? Oh, yes. So that's actually by coincidence the same answer as this. But remember, this distance is from the centres.
Yeah.
So if you were to wondering what the heck has just happened, from here to here, that's 385,000 kilometres, which actually is the same number for the distance where the forces are balanced. But remember, when we measure force distance, we measure from the centre. Oh, but that was from the centre as well.
Yeah.
Oh no, I must have typed in something wrong then. That's a ridiculous answer.
I think it there is the bottom part.
What?
You have to split that.
Oh my goodness. Disgraceful. Is that okay?
Yeah.
Right. Okay, what's in here?
5.94.
97.
Yeah.
10 to the
24.
24?
It's not 10. 0.
Uh, 10.
Yeah.
Right, that's better. 3, 4, 7,000. Mistake?
That's it?
Yes? Shamsa? Are you sure? This is okay? 3, 4, 7,000. So, from like here to here, 3, 4, 7,000 kilometres. That's this point here is when the two balance. Yeah, to just zoom out, is it? Is that what you got? Or what did you get?
I didn't calculate.
You didn't calculate?
Because, when I spent them, then was the number was...
Oh, here?
Yeah. I just got an idea.
I've seen this question in the exam twice.
I got it different. I got 373,951.
373?
3951.
I don't think I mistyped anything.
Is it because I rounded off early on?
It could be. I like to keep my calculations as late as possible. So I like it when I can get everything down to a single formula at the end, and I just put the numbers in. Now it's weird because flipping person who writes the exam doesn't like this. He prefers what you do, which is get as many calculations done early. I prefer the complete opposite, which is leave all the calculations until the end if possible. It just makes it more accurate.
Yeah, I like this way.
I know, but he doesn't.
Why? Stupid.
I don't know. He's kind of, he's my enemy.
Your enemy.
Huh? I don't know if he hates me. He doesn't like me, perhaps.
But his way is not good in the, to calculate, but the number is so messy.
What can I do? He's up here, I'm down here. I'm just a simple physics teacher. I have no power. Okay, continue.
The question before.
Yeah.
Did you convert from
Did I convert?
kilo to meter?
Oh, I believe I did. I hope I did anyways, yeah. Yeah, I was, Wookie reminded me to put in the 3 zeros.
And mine is here.
And here, yes.
Yeah, so but in the previous question.
Did I? What was the previous one? Oh. I hope I did. I think I did. Wait, actually, I might still have it here. 29.8 kilometers per second. Yeah, I think this seems like the right answer.
Yeah.
No, that'd be too slow, actually. 29 meters per second. Yeah, no, that seems right. Yeah.
What are
The distance between the Earth,
Full distance.
the full distance between the Earth and the Moon. Yeah. So, like, I have x and or minus x then. Is this okay, guys? We can continue or not? It's okay? Yeah? Okay. So the next one. What is the gravitational field strength due to the Earth on a plane which is 10 kilometers above the surface of the Earth? Alright, so that's just a calculator problem. What's the formula? It's G M, which is mass of the Earth,
Yes.
which is 5.97
By 10
pi 10 to the 24. Whoa! Over
R
r squared. Yeah. Now we have to be careful here. The radius is 6371000 plus 10,000. 10 kilometers.
Yeah.
The plane is 10 kilometers in the air.
Yeah.
So I'm expecting an answer smaller than 9.81.
Yeah.
9.79 about. So if you remember that experiment we did where we calculated the G, yeah? The next time you fly back home, if you could bring the pendulum on carry-on luggage, and when the flight has reached its 10 kilometer height, you can perform the experiment and you'll get a smaller value of G. Yes, you can test it for yourself. And it only gets smaller as you move higher. Yep.
Teacher, the question on the previous question.
Yes.
For the x distance between the spaceship and the Earth, do we need to minus the radius from the Earth itself?
No, the distance I gave you, Wookie was actually asking me this at the start, I wasn't being clear. You usually give distances between planets as from their centre to their centre. Anyway, so that's normal. Yeah. Okay, the next one. What is the gravitational field strength due to the moon on the surface of the Earth? Okay, so just to explain what's happening here. Here is the Earth, and there's obviously a gravitational field here caused by the Earth. But if we imagine the moon up here, the moon also is pulling on you. You're inside the moon's gravitational field. So there'll be a small g due to being inside the moon's gravitational field. How big will that be? Well, again, that would just be gm over r squared. But this time, the m is the mass of the moon, and the r, we have to be careful, is the total r minus the radius of the moon.
Why moon?
No, Earth. Because we know the distance from here to here, so we should minus that to get it from here to here. Okay. So what do I need to it's gone. No.
Cancel everything.
There we go. Right, so let's type that in. 385000 minus 68. What's the Earth?
I think 3, 4, 3, 8, and then 0, 0, 0 more.
385000
Minus 6, 3, 7, 1.
000. And then the mass of the moon?
7.34 by 10 to the 22.
Okay. I'm expecting a small number here. Whoa, this small? No.
Something wrong.
Well.
Don't think for the
Say again?
should we square the radius?
Is it not square in the formula? It is squared, yeah. Have I got enough zeros here? 385000 000. Well, if that's the answer, that's the answer.
I got similar.
You did?
Yeah.
Okay, it's tiny. 3.42 times 10 to the minus 5 newtons per meter. Tiny.
Yeah, so similar but not exactly same. Why is not same? I use the J 6.67.
Oh, this G is more accurate. There's more numbers in it. It's okay. Yeah, continue. So, now, here's the last one. A rocket is fired into orbit. It's slightly above the surface of the Earth and is breaking through the atmosphere. The engine's about to be cut off. How fast does the rocket need to be travelling at so that it can escape the pull of the Earth? Hint, the potential energy will need to be zero, which comes from the kinetic energy. So, what I'm imagining here in my story is you have the Earth and you have the atmosphere around the Earth, and there's a little rocket here, and the engine is about to turn off because, you know, it used up all its fuel. Because, you know, when you've seen rockets launch into space, most of the fuel gets burnt up inside the atmosphere, and it's practically all gone when it gets outside the atmosphere. So we would like it to be going fast enough so that it doesn't fall back into the Earth, so that it can be free. Now, at this point, it has kinetic energy and potential energy. Here, it has only kinetic. And it doesn't really have potential. Why not? Because it's free. And we don't want to waste energy. What I mean is, we don't care if it's going fast or slow. We just want it to be free and moving. So we'll say its kinetic energy is nearly zero as well. We don't care about how fast it's going. We just want it to have positive energy, so it's free. It's not trapped. Okay. So maybe if you want it to be going very, very slowly, this will be a small number. But it's so small, we don't really care, so we'll say it's zero. Here, its kinetic energy is a half mv squared, and potential energy is minus g mm over r. And we want this to equal 0 plus 0. So we get m's cancel. V equals 2gm over r square root. Here, oh, this potential energy is negative because it's trapped. So it's like Ke plus a minus Pe. Yeah? Now, what do we put the radius in? I never actually said what the radius is. But when we look at it, okay, this distance here is like 6371 kilometers, whereas the atmosphere of the Earth is something small, like only like 10 kilometers. So we can roughly say it's just going to be this, and forget about this. Okay, so let's see what we get here. 2 times g times, what's the mass of the Earth?
5.97 by 10 to the 24.
And then the radius? 6371000. Okay. 11.2 kilometers per second. That's, you know, that's fast. 11.2 kilometers per second. But if it was going this fast, it would not fall back to Earth. It could escape the Earth. Yeah.
See, when are they still after they pass through the atmosphere? How do they move after that?
Well, it depends what you want your satellite to do. So do you want it to be in orbit, or just to escape, or what? Well, if you want it to be...
Why is it going to the moon?
Yeah, what they do is, it burns off the fuel as it leaves the Earth. So it starts to slow down as the Earth is pulling it back. So it slows down, and what you want is, do you remember this question we did earlier? As it leaves, there's no more fuel burning. So it'll slow down. And what you want it to do is to stop after this point. Because even if it's 0 meters per second here, because it's past this point, then the moon will take over and pull it in. So you need to make sure it goes fast enough to reach here. So, yeah?
Is the moon will it crash?
Yeah, so like you have to make sure, like usually what they do, I think, is when they launch it, they put it at an angle so that it starts to come in, so that when it gets to the moon it's perpendicular, and so the force pulling it in can become a circular force. Eventually though, its orbit will decay, eventually. Maybe after, these satellites, I think 10 or 20 years, and then the orbit collapses. So you might want to keep a little bit of fuel in it so that you can... Is an astronaut? Yeah, they have to bring enough fuel to go back.
It works the same way?
Yeah, but it's better going back. The reason it's better going back is if you start here, you only need enough fuel to get to here. So even if you're 0 here, then the Earth can pull you back. So, in other words, moon to Earth is much, much easier than Earth to moon. There's also a second advantage. The moon has no atmosphere. So there's no friction when the rocket leaves. So the only force it has to worry about is the moon. But that's actually quite small compared to the Earth. Going back is easy. That's much, much easier than going to the moon. Much, much easier.
But to reach that point, isn't it hard?
Oh yeah. Not many countries have done it. It's quite hard.
Include Ireland.
No. No. America have obviously done it. Perhaps China will be the next country.
Yeah, and
Or-
Russia.
No, if I was to bet money, I would bet on China.
Why?
Yeah. I don't think Russia is as organized enough as China to accomplish this.
Didn't Russia go?
I don't think they've put a person on the moon, like on the surface,
Where did it?
Huh?
Where did it?
I don't know, I have to check actually. Like places like China, Russia, India have definitely put satellites into orbit
Astronaut into the moon?
and astronauts into orbit, but I'm afraid it's only been USA that's made it here.
To the moon?
Yes,
Really?
yeah, just USA. In 1969. Okay.
So going from the moon, there's no traffic. There's no.
No, there is, but it's so small compared to what you have to deal with Earth. It's much, much easier.
How long does it take?
I think it's about, it's like 4 or 5 days, the journey.
From Earth to moon?
Yeah,
What?
yeah. I think so. 4 days, I think.
In Earth time?
In Earth time,
Yeah.
Well, I don't think 3 months.
Months? Ah, come on, it's not that far away. In 3 months you can get to Mars.
Did anyone go to Mars?
Not yet. Not yet. Huh? Is it 7 months for Mars? It could be, or could it be 7 months there and back? Oh no, maybe it is 7 months there actually, yeah. 3 months seems a bit too short, doesn't it?
Or did you
Yes, no problem. 4 days, you're at the moon, no problem. Absolutely. Okay. We can close this, yeah?
Can you go back to the question?
Yes.
And actually, the answer
On the calculator or
in me.
this here, yeah? Oh no, sorry, that was the last one, yeah, sorry. You want
Yeah.
this one here, yeah. Okay.
Are they gonna send anyone to Mars?
I don't know, to be honest.
Why?
Well, okay. In my head, it's not if, it's just when. Well, this is the thing, you know. If I said to you, yeah, they're going to send someone to Mars, you might say that's great. But if they send someone to Mars long after you're dead, then it's like saying no.
But they are doing research now already.
I know, but imagine the year is 1969. Okay, just imagine it's 1969, and you just saw Neil Armstrong, July 21st, 1969. You just saw Neil Armstrong, first man on the moon. And then I ask you, how long until you think there's somebody on Mars? Would you say 2025?
1969.
I think if you ask somebody in 1969, how long until you see somebody on Mars, they might have said 1979. Or even maybe 2000 at most. They would not have said 2025. So my point is, maybe you say 2025, but really it'd be 2050.
I still be alive.
You never know. No, you don't know. You don't know.
Wow. They chose the people on that.
No. Until they start building something, that doesn't matter.
They did it.
Yeah?
I think so.
Mm.
I wasn't interested. I wanted to go.
Yes.
No, I wanted to
I
go.
think you can pay to go.
You can't pay to go into space, correct?
On the moon?
Not the moon, just into space.
How much?
Well, I think it's something like, I think Virgin Galactic, Richard Branson's company, I think it'll cost you maybe, I don't know, like 150,000?
It's like
200,000, something like
the
that.
rocket, is it like luxury rocket or is it like the normal?
No,
Oh, you're
I
paying
think
$100.
the rocket holds something like maybe 9 people or something.
I know, but I feel like first class service.
I think every seat is first class on a rocket
No,
into
I
space.
mean like you got champagne, tea, everything. Things for you.
No, I don't think so. I think the experience is going into space, not if you get champagne.
Yeah, but then
Yeah.
you
Yeah, I'm sure there'll be champagne when you land, but I think they'd be more worried about you not dying on their journey. All right, did you write this down? Yep. Okay, we'll close this and continue then.